we will pioneer another proof today. Reinventing the Taylor series using integration by parts. Now, to begin this proof, let's look at the fundamental theorem of calculus. As you can see, you have an expression for f of x if you rearrange the variables, and that term in there, you could express it as itself multiplied by 1, and you could use integration by parts to expand it. Interesting. And now we take that expression and actually apply the integration by parts. Yeah, cool animation. So, as you can see, we're keeping this general, so we want to have a C right there. So, the future version of myself, for many moons in the future, will explain to you now how you can apply integration by parts an unlimited number of times. So you start with a general rule for integration by parts, and now you have a specific function that you want to expand using the integration by parts. And now we see that it follows the same form as the rule, so we can expand it right over here. And so you'll actually notice that that term on the end can also be expanded because it follows the same general form. And so we can actually apply this an unlimited number of times because now we're back to that same form. It's just nested. So it doesn't matter which iteration you're on, you can just still apply it whatever you want, which is pretty cool. So in the previous slide, we saw that we could use integration by parts as many times as we want, which is very important. And also, C can be any value that we want. That's also very important because you'll see that later. And I just want to stress the fact that C could actually be any function of a vector v, such that v does not include t, because it has to be a constant from the perspective of t. All right, so we have this term over here, and we have, upon further simplification, we can see that within those square brackets, we have two terms that both involve c. We have a derivative evaluated at x on the left, multiplied by x plus c, and a derivative of evaluated at x naught, multiplied by x naught plus c on the right. So what we're going to do is that we're going to choose a value for c such that one of those two terms are eliminated, because we want things to get simple, not more complicated. So we could either choose, negative x to cancel out the one on the left, or a negative x naught to cancel out the one on the right. So which one do we want to use? Well, of course, using Occam's razor logic, we want to do, cancel out the one that causes the least amount of problems, or, the more simple one. And we can see that on the right-hand side, we just have a derivative evaluated at x naught. So it's just going to be a constant. So that's a term that we want to keep, because that's going to be a whole lot more simple than a derivative evaluated at x, which is going to be a whole lot of, complex terms, all this stuff. So we're going to choose negative x to be our c value. And so we have this over here. The left side cancels out. And then we have this over here. And it simplifies to the derivative of f of t with respect to t, evaluated at t is equal to x naught multiplied by x minus x naught. and the c value is negative x over there too.
And here's the results of the first integration by parts over here.
So we proceed with the second integration by parts. And we expand the expandable term, and we get this right over there. And things get a whole lot more simple if we just set c to equal to 0. There we go. We shall proceed by distributing the minus sign. And we shall proceed once more by evaluating the integral, eliminating the 0 term, distributing the minus sign. At this point, your eagle eyes may have noticed that in this term you have an x naught minus x instead of an x minus x naught like you had it on the previous term. However, this could be fixed because x naught minus x is equal to negative x minus x naught. And so then if you square that, the negative signs cancel out, and thus you can reverse the terms right there, so that you have an x minus x naught right there.
And then here's the results of the second integration by parts.
So at this point, believe it or not, we've pretty much reinvented the Taylor series. And you may be wondering, what do you mean? Where's the formula? And my answer to that question is that the whole point of the Taylor series is to create a polynomial approximation of any arbitrary function. And now we have enough information to create a procedure that we can program any computer to follow so that we obtain this special polynomial. And all we really need to do to invent a crude yet fully functional procedure, at a bare minimum, is to take the fundamental theorem of calculus, rearrange the formula to solve for f of x, apply integration by parts to the expandable integral term at the end, choose the integration constant to be negative x, and then just continue to expand with all future integration constants set to equal 0, just as we did it in the second integration by parts. And as a result, we're going to obtain an unsimplified and messy polynomial, but still a polynomial nonetheless, with the integral term at the end. And then we just have to just eliminate that integral term, just drop that integral term, and then boom, you've got the Taylor series approximation.
So one thing I forgot to mention is that t is actually a dummy variable. So it can be anything including x. And that's going to be important for generating the Taylor series using your function f of x.
So I'm actually going to end the video here. And I originally had more planned, but I just wanted to show you how the Taylor series is built, using the fundamental theorem of calculus and integration by parts, as well as setting the integration constants to the correct values. And that's all you really need to develop the procedure for making the Taylor series. And in part 2, I'm actually going to find an algorithm that's going to be a whole lot easier to input into a computer, because it's kind of hard for a computer to you can't just say, hey, computer, integrate by parts, So in part 2, I'm going to provide, more concrete formula that a computer can process each time you want to expand the polynomial. And so that's going to be pretty cool. And that's the reason why I included the second integration by parts in this video. And also I included it to show you, the procedure for how you would go about doing the integration by parts after the first time. And you'll actually see that, the second integration by parts is actually pretty important for recognizing this pattern and developing a more concrete algorithm that is ever so slightly closer to the actual formula for the Taylor series. And that formula is actually something that's, very simplified. It's the final formula in this process. And it's actually a whole lot more difficult than I thought. Now, I thought it would be pretty easy to get the Taylor series formula, but it's actually kind of difficult. I didn't really realize that. Oh crap. I forgot the animation. Whoopsie. Oh yeah, and also I was going to mention the multi-dimensional Taylor series in part 3. And just as a hint, you actually use the directional derivative to obtain the multi-dimensional Taylor series. So you just like combine the directional derivative with what you just, with the formula you got from the one-dimensional series. And so that will be in part 3. Alright, so that's it for part 1, and thanks for watching.